infrastrukture se zaveda različnih prednosti in priložnosti v panogi. Mr. Lovat, I invite you to share with us your rich experiences. Thank you.
Good morning. My English is maybe easier to understand than Arnold's. Even I don't understand his English sometimes. I'm a Canadian speaker, and our English is clear, but because of our cold climate, I tend to talk quite quickly, so I apologize to the translators. So, as Arnold was talking about Slovenia and dinner last night, I also have a certain experience of Slovenia. I think this is a brilliant, brilliant marketing position that Slovenia has taken. I feel Slovenia, I feel love, and I am one to say that I have been coming to Slovenia for 40 years. And you may say, well, why do you come to Slovenia for 40 years? Because in 1984, I married a wonderful woman by the name of Angela Košir from Ribnica. So I am coming here quite often to visit family, and I'm very proud to say that I feel part Slovenian. My wife, who's a wonderful woman, she gives me a little more love than I need sometimes when I'm not doing the correct things. She's a very outspoken person, but she's a wonderful woman, and she's become a very kind and warm stara mama at the same time. So I'm here to talk to you today about my experience in urban tunneling. I am a TBM manufacturer, so I'm usually the last one on the list when it comes to contracts and initiating works. So we have a very practical way of doing things. I'm a mechanical engineer. Are there any other mechanical engineers in here? Please hold up your hand. That's what I thought, none. So, so in my world, if it doesn't move, I'm in trouble. In your world, if it moves, you're in trouble. So we are very much detail-orientated people. We're always looking to innovate and create new solutions to problems. So I may be going a little deep into the weeds of technology, but that's what we mechanical engineers do, and I'm hoping to convey some vision at the same time. So tunnel boring machines, or TBMs, are generally larger than 3 meters in diameter, used for sewer, metro, and rail tunnels. Urban tunneling is construction of tunnels in a densely populated area. The challenges it brings: the tunnels are shallow, which means they're in soils, soft ground. We have to deal with existing structures, either on the surface or underground. And the perception is tunneling is risky. And the only reason that is a perception is because negative results sell media. We don't provide enough information of our successes that we do around the world, but there's this perception. Perception is also disruption on the surface, noise, and traffic congestion, which is really not the case. Tunneling is where project owners require a product, a tunnel, with a reliable price and schedule. Owners, designers, contractors, and suppliers of TBMs all have commercial interests. We're in business to make money. End of the story. Project cost is extremely sensitive to schedule. There is a high capital investment into the project to get the project up and running, but when there are delays in the project, the costs actually skyrocket, become disproportionate. So, if we improve the schedule, we save money. A stop TBM is extremely expensive, and usually we mechanical engineers feel the heat first when we have a machine that is stopped. Tunneling is years of investigation, design, and planning. Years. It's just not something that happens when you buy a TBM and put it on the ground. There's a plan. Once a TBM is fabricated, brought to site, it's relatively inflexible. So therefore, you go back to the first point: planning, planning, and planning, and planning. And I will say this many times during this presentation. In the beginning, 100 years ago, this is a project in Canada. You see the means of excavation, manual, haulage of material by a donkey, a segment erector. Today, we have a very complex mode of excavation, cutting heads, excavation material out by a conveyor, and the same in concept segment erector. In 100 years, we moved forward quite quickly on the innovation side, and predominantly this was done in the 70s, in the 80s, and 90s. Since the 2000s, and it goes back to what Arnold is saying, on these contractual arrangements, we have become quite stagnant in terms of our innovation on tunneling machines. One thing we have done is we've moved the size of machines further, larger, and larger. In the when I graduated university, this was a big machine, a 6-meter machine. And then, oh my God, who's dreaming a 10-meter machine? Who's crazy enough to dream of a 10-meter machine? Mechanical guys. So we ended up building 10-meter machines, then 12, 14, and now the standard is up to 17, 18-meter diameter machines. Today, the 13, 14-meter machines to 10 meters is the norm. You can have a high level of confidence in these size machines. The development of this technology has been by quite a large group of people. We in North America, we're developing our own. The Japanese leaders in the 80s, 70s, and 80s of the technology. Many of the things that we are using today have originated in Japan. The Europeans, specifically in Germany, also running their own program on developing machines, as well as the British. Today, the center of activity is coming from the Chinese. They are the ones who are developing, innovating, mass-producing these machines. So what tools do we have when we go into soft ground? We have basically two tools that we have to choose from. And they're quite similar, but different in the way that they achieve the goal. The goal is constant pressure. These are submarines. They really have to think they're a submarine. They're not an excavating tool, but they are a submarine which has to create pressure in the front and completely around the shield of the machine. And how do we do that? There's two methods. One is what we call an earth pressure balance machine, which uses the soil itself to create the pressure against the face. The other, a slurry machine, which uses bentonite to pressurize the face with an air bubble. The mode of transportation of muck is through hydraulic transport. So we have to decide which one we're going to use. More detailed look of a slurry machine, we use compressed air, which is pushing like a shock absorber in the liquid, which is pushing against the face. So this type of machine is always under pressure, and it's very suitable for materials that are coarse, such as sands, gravels, etc. Earth pressure balance machines use this screw conveyor to meter for every revolution. It displaces muck, and the machine moves forward. The problem with the earth pressure balance machines, because they don't have this shock absorber effect of the air, we have to introduce it. So we have an external tank, which is located on the backup of the machine, which does exactly the same as a slurry machine to provide this air pressure, keeping the entire shield and face under pressure. Soft ground tunneling is, when I graduated university, a client of mine said, basically, you have to excavate the soil without the soil knowing it's been excavated. You do not want to change anything around the soil as it's being excavated. Tools that we've developed, again, starting out of Japan, was the ability to add additives, chemicals to the face of the machine to make the soils, to treat the soils so they are more fluid and being able to be digested by the machines and continue to maintain pressure. There's a number of components that we're using. Foam, which is no different than the foam that we use for shaving in the morning, soap and water and air. Polymers, which is the same type of polymers that are in babies' diapers to absorb water, and bentonite. So these are three things that we inject in the front of the machine, or there's an art to all this, where we combine the three and utilize the three for different purposes in different geologies. And this is an art, and this is some expertise that comes from the site. It cannot be planned. It's quite difficult to be planned in advance, but we need the tools on board the machine in order to achieve combinations. Through these combinations, and this is for the geotechnical people to make you happy, so we have basically a particle distribution curve. The blue area was the traditional area in which earth pressure balance machines were being used. With all these additives, we move the application further across towards the gravel, towards the area of slurry machines. And here are a number of projects on the right, here in Europe, in which they use this technology of earth pressure balance machines with additives. This also means when we're doing additives, using machines, the machines are inflexible once they arrive on site. We must do our homework on how we're going to use these additives in the machines. Machines, tunnel boring machines, are not laboratories. They're not to be put on site and then start the testing of different materials and how they react with the geology. Far too late, far too late. And any failures or miscalculations on the additives have consequences on the machine, such as clogging, and then you can spend 2 weeks to unclog the cutting head. So laboratory testing, and these are two famous universities here in Europe, Politecnico di Torino, and this is Bochum University in Germany, and basically they have a simulation equipment. This is a screw conveyor. They put material in here under pressure, additives, and they test which additives work with the geology that has been shipped from site. And this is what we really look for, this type of consistency of a toothpaste. And this type of work must be done in advance. Earth pressure balance machines have one extra bonus that they have going for them. Traditionally, they're working in this pressure mode, where the screw conveyor is keeping the cutting head chamber and the face under pressure. However, if we hit very good conditions where the ground is standing up, a soft rock, for example, we can profit and only use the screw conveyor as a transporter device to take material from the cutting head to the conveyor belt, which increases the rate of penetration, which means an improvement on schedule, and reduces wear on the cutting head. So this is, if we run into this type of geology, then we have this ability to profit from it. So what is the use, the worldwide applications of between slurry machines and earth pressure balance machines? Today, 90% of the tunnels in the world are being bored with earth pressure balance machines. There's no doubt that slurry machines, they have their purposes. It's a narrow band of coarse material, high water pressure. There's no doubt they have an application. The earth pressure balance machines are very much more like a Swiss Army knife. They have all kinds of tools that pop out of it, far more flexible. We can adapt its application as we have changes in geology. Heron Connect has come up with a solution between the two, which is known as a variable density machine. And was developed in Kuala Lumpur. It's been used in Berlin, where he uses both a screw conveyor and a bentonite slurry system. Both systems are being used on the same machine, which requires a conversion. This will have applications in difficult geologies with wide spectrum changes from clays to gravels. The point I made earlier on, pressure, pressure, and pressure. It cannot be repeated enough. We, and it would mean the contractor, the owner, the geotechnical people, even the mechanical guys, we tend to focus on the face of the machine, the face. However, this machine is 15, 17 meters long, a day's production. It takes a day's production from the cutting head to when the segments are permanently placed, 1 day. And in that day, over the shield itself, there's a gap, because this machine actually has to move. Then there's another gap in the back where the segments actually are installed. And it's absolutely critical to keep this zone under pressure. We have seen, when we watch sediment curves, that the settlement is actually in the back of the machine, not in the front of the machine. We control it in the front, but then we lose it in the back. So there's far more focus now, today, on the shield and on the tail of the machine to virtually have zero settlement. So the main point that if I could say, if I was a TBM manufacturer and I'm going into a project, is know your geotech. The ground is the boss. You cannot win the fight if you try to impose your methods onto the ground. You must understand the geology. And I look at it, how does the geology behave? How does it interact with the machine? I'm not a geotechnical engineer, but I know what I need to understand how to get the best performance of the machine. The more information we have, the better it is. And the biggest surprise is obstructions. Obstructions is the killer of TBMs. And we've seen a number of times where tiebacks, sewers, any type of man-made object in the front of the machine, well, that's bad news. And it's a problem in the industry when cities were built in the 50s and the 60s and 70s where there was not good documentation of what infrastructure that was put into place. But it's critical to find out if there's any potential obstructions that may occur in front of a machine. And I will say this, I mean, I know there's a lawyer in the room, so I'm being very careful. I will say TBMs exist for all conditions. You know, since as a lawyer, I'll say most because I don't want to get myself into trouble. But I'm a believer that basically any geotechnical formation can be solved with a tunnel boring machine. So we focus on this piece here. This is only part of the discussion when you're tunneling in an urban environment. You have this process where you take the material out and you have to load it on a truck and take it away and do something with it. In the opposite direction, you have to bring the segments down into the machine. Tunnel boring machines are much more than a machine. This is just one page that I wrote out of systems that which are on a tunnel boring machine. It's not a machine, it is a factory. We have to stop calling them machines. It's not a bulldozer or a backhoe. It is a factory. And what we do is build a tunnel behind it. There's so many interlocks inside today's tunnel boring machines, it's a factory. So the factory approach must be taken. Prior to starting up a factory of anything, there's all kinds of testing that goes on. And we must be treating the tunnel boring machines exactly the same way. Test, test, and test. Developments that we are doing recently, we historically have been using rail transport to bring materials in and out of the tunnel, muck boxes to bring the muck out, segments go in with rail. The production, unfortunately, was tied to the quality of rail in the tunnels. And because it's a temporary build for tunneling only, many contractors wouldn't focus on the quality of rail. It would lead to derailments. Derailments mean stopped production. So again, this is part of the process. And what we've been able to do in the last few years is there are manufacturers who've developed rubber-tired transport, meaning everything is going in and out on trucks, on rubber tires. But the real reason that this has been able to be achieved is that we use continuous conveyors now to transport the muck. We do not take the muck out on muck boxes, but on continuous conveyors, because the muck and the segments are going in opposite directions. So now these two activities are separated. They're separated, which gives us another boost in productivity and removing the noise. The loudest thing that you would hear in this tunnel, this is, at the time was the largest tunnel in the world in Seattle, Washington. The only noise you would hear is the truck honking a horn. Otherwise, it's just a small little hum from the continuous conveyor. So the noise, which is a health and safety issue for tunnelers, has been reduced. So I go back to the same project, Alaskan Way Viaduct. This is the tunnel, 17.5 meters in diameter, two-lane highway, which was to replace this viaduct right up against the waterfront of Seattle. This is an example of instrumentation and what it can do for us. So the tunnel alignment was running parallel to the viaduct and eventually had to cross underneath the downtown through various buildings. The deal was the viaduct, which we are replacing, must stay live while the tunneling operation is going on. It was only closed for 3 days while the TBM actually crossed underneath of it for 3 days. So there was always obviously concern about settlement on the viaduct. So the viaduct was standing on pillars with micropiles underneath, and here's our tunnel that goes underneath of it. Here's the supports. So it was decided to come with an elaborate scheme of jet grouting to isolate the tunnel from the viaduct. When we approached the viaduct, the instrumentation that was spent on this project was astronomical, probably over the top, but extensometers in front of the machine, and we knew what the pressures were, the densities of the material. on site was like a command center. It was like it's like being at NASA. All these screens, we can watch exactly what the machine was doing and have an instantaneous feedback from the extensometers on how the ground was behaving 1 meter above the tunnel. We knew exactly how the ground was moving, and we approached the viaduct with basically zero settlement. We went underneath the viaduct with zero settlement, and we went under these other buildings with zero settlement. And that was all due to an investment on instrumentation. So these machines can do wonderful things, but you need to be able to monitor and measure things. Once we passed under the viaduct and spent all the money on instrumentation and on jet grouting, we tore it down. I mean, so it's, when we look back at it, we say perhaps we didn't have to spend that money, but hindsight's always 20/20. And this is the point I'm making with respect to information. The amount of information that comes off these machines is of value that needs to be read and interpreted by the right people. This information is not for when something goes wrong and to try to find the root cause. It's to be proactive and help to solve the problems before they happen. So we moved to site, the back end of the machine. So this is an 11-meter machine with its entire backup, 150 meters long. These are not small factories. They're quite long. And in the station or portal, there's always a continuous conveyor to pull the muck out. So we need space when we assemble these machines. We need space. This is a typical plant layout. This is Sparvo, which is between Bologna and Florence. The site, 4 tunnels, highway tunnels that were built. So this is a segment plant, concrete segments, and 5 areas to discharge material for drying. We need space. So if we're planning a tunnel in Ljubljana, which I think we are, we have to consider all of this. Where do we put this infrastructure to support the monster? There's always a perception in the industry, the critical path goes through the TBM, and we must order this TBM as soon as possible. No, it never goes through the TBM. It goes through the segment production. You have to order design a ring, order the forms, set up a factory, start production of the segments, and store them and let them cure. The critical path goes through there, never through the TBM. TBM manufacturers can react quite quickly. And the haste that goes on to ordering TBMs comes back to haunt us at times. Take your time, have the right geotechnical information, and design it properly. This is a project which is in Switzerland, Botsburg, where we see this is a 12-meter machine assembled right beside a railway line. And the reason it was beside a railway line was for logistics. Material in, material out. And this is the biggest challenge we have with TBMs. Not the technology at the front end, but the logistics behind the machine. So if I was planning a tunnel in Ljubljana, for railway purposes, perhaps a tunnel with 2 trains in 1 tunnel. Here's the downtown, the center. There's a wonderful area just to the east, which makes a perfect logistics site with respect to rail network. Pulling everything away from rail, keep it off the streets, feed it at night for your daily production. And this would be a very nice solution, keeping away from downtown, keeping the trucks out of downtown, and you can achieve 2 long bores from 1 logistic area. So everything I said in the last 20 minutes, tunnels are the sustainable solution for the development and improvement of cities. There's no doubt about it. They connect from A to B. No one, have you ever heard anyone complain about tunnels? No, once they're built and they're operational, everyone's extremely happy with them. Tunnels have been in existence. If you look at Paris and London, when they put their metros underground, everybody's ecstatic about their metros and proud of their metros. So there's never any argument once it's done. Know your geotechnical conditions, and this is for everyone. Too many boreholes never hurt anyone. Too few can be painful. Investigation, design, and planning. It's a process. It's a factory. You stand back and cooperatively everyone designs this process. The construction is just an implementation of the plan. It just happens. You have to stick to the plan that you've designed. Site staging, TBM tunnel logistical plan. From the segment production, is what I was saying before, to the tunnel face, to the muck disposal. What do you do with the muck disposal? Once the muck is dried, coming out of an EPB machine, it can be reused for fill. So this is something to be considered, the reuse of the soil. Site staging, out of the city center. Keep the trucks out. This is a planning issue. This is a planning issue. It's not a construction issue, it's planning. Keep it outside the city center. Instrumentation, stabilizing and monitoring is the key part of the process to have zero settlement. And again, TBMs exist for all conditions. I cannot see how the industry cannot react to any difficult geological formations. TBM manufacturers, they have hundreds of machines in the field. They've done thousands of projects. They have many tools and a vast experience, which goes underutilized during bidding staging and design stages. Use this as a tool. It's an experience that I'm going to say it, contractors and designers don't have as deep. TBMs have been in trouble, there's no doubt, but we've always get out of trouble. So use that experience. Contract terms to encourage open and innovative solutions. We have become stagnant in the last 20 years, but we need a means of contracting. We've heard it somewhat from Arnold, that's open, everything is on the table. The machines that I have seen that developed the fastest and new ideas is where it was an open commercial arrangement, sharing the risk. And at the end of the day, it's people who make tunnels, not TBMs. So you need to invest in the people with experience. Thank you very much.